Today's problem of the day: smallest greater elements in whole array. Okay, so given an array A of n length, we need to calculate the next greater element for each element in a given array. If the next greater element is not available in a given array, then we need to fill minus whatever be this number, a very small value at that index place. So the first example, we are given array 13, 6, 7, 12, and between in this array, like 13 is the largest. So that index, we are not having any greater element. Okay, smallest greater element, we are not having any smallest greater element. So 13, in that place, like we have to put this small number minus 10 lakh or ones, tens, 100,000, 10,000 lakh, 10 lakh crore, minus 1 crore. That's a very small value. For 6, then the greater elements are 7 and 12, but from them 7 is the smallest. So in this place we have to put 7. Now for 7, we have 12 and 13 as the largest. It doesn't specifically says that it has to be the next greater element on the right only. No, from the whole array we need to consider the whole array, not like we consider 6, then 7, 12 only need to be considered. We also need to consider 7, 12 and 13, and from them 7 is the smallest. So that's how we need to consider. So for the last element 12, normally in the next greater element, like we will be only looking to the right. So at that time, like we will be saying there are no elements, but that's not what this problem says. We have to consider the whole array. So if we consider the whole array, there is an element which is greater than 12, and that is 13. So at that position we need to put 13. So same way for this one also, and if we consider 10 raised to 5 and small value, and we need the time complexity, expected time complexity in n log n, but don't care about it. So let's consider the first 13, 6, 7, 12. 13, 6, 7, 12. So if it is like find the next greater element to the right, it is pretty straightforward. Like we will be making use of a stack, adding the element to it, popping it if it's larger or smaller based on upon the question that we are asked. But here this might not work because we need to consider the whole array. If we consider stack, if we somehow get rid of this 6, and there was some 5 here, and there was 6 in our stack, and it gets popped out due to the action of some of these elements, but we are having a 5 at the very end, and the next greatest element, which is the smallest, is 6. So our answer has to be 6 in this case. But if we make use of stack, that 6 has been gone. It has been gone. So it will not give us the correct answer. So the idea that we need to imply is, let's give rank for each of these numbers. So let's sort it. After sorting, we have 6, 7, 12 and 13. Let's give some rank. This is rank 0. It's for the smaller number. This is rank 1. This is rank 2. This is rank 3. So now we start traversing, and we store this value to a separate array. Okay, this is a separate array. This is just we are copying. At first we are copying this to a copy array, then we are sorting that copy array, and we will be getting this one, and we can consider that its indexes as each of the numbers rank. Okay, now let's see, we are at 13, and we can look inside this array where we can see 13. Okay, where we are seeing 13. This is not 13, this is not 13, this is not 13, and this is 13. Okay, at that time we need, so what will be the next greatest element after sorting? It will be that element just coming the next element, because if we find this is to be x, the next greater element will be x1 plus x plus 1th element, but this 13 is the largest among them, and x plus 1th goes out of bound, so that has to be separately handled. So at this position we get that small number. Okay, the small number, it might not be this one, I just indicate this will be the small number. Now we go to 6 and we find which is the index that we can see 6, and the index is 0, so we need the next number. So suppose this is x, we need x plus 1, 1th element, and this x plus 1 is not out of bound as we seen earlier with 13. So the x plus 1th element is 7, so we put 7 at that in the result array. Now we are at the next number, it's 7. Okay, so 7, we again start traversing from here, 6, 7, yeah, it's equal to 7, so we get our x as 1, and we need 1 plus 1th element, which is 2, and this 2 is not going outside, out of the bound. So what is the element at that position? 12, so we put 12. Now same way we are at 12. Now we check where we can see this 12. 6 is not equal to 12, 7 is not equal to 12, and 12 is equal to 12. And now we need to find 2 plus 1th element. What is 2 plus 1th element? That's the third element, the element at the third index, and that is 13. So we will be returning 13. So that's how we will be doing. But here there is a problem with our time complexity. Whenever we are here, we are making use of a big O of n square approach. Like when we see a number, then we are going through the sorted copy array each time in order to locate the position of that array. Again we go to the next element. Again we search inside the sorted copy array. So it's kind of extra space, extra time. Big O of n square will be the time complexity of the case. So we can like what we can do, we can make use of an extra space actually, which will be having a faster lookup, and for that we can make use of hash map. So let's see how we can see the hash map. So we sorted. Okay, we sorted. Now as I told, like we can make use of a hash map, and its key will be the element, and its value will be that index. So after sorting, like we will be storing those values. 6 is found at 0, 7 is found at 12, 7 is found at 1, 12 is found at 2, and 13 is found at 3. Okay, now what we need, whenever we are traversing, we just need one traversal through this given input array. Let's see, we are at 13, and we just look into this hash map. What is the index of 13, which is given as a value inside our hash map? It is 3. So we just check whether 3 plus 1 is greater than or equal to the length. If it is the 0 indexed, we are considering 0 index based array. So if 3 plus 1 greater than or equal to length, the length is 4, so 4 is greater than or equal to 4. So that means this is the greatest among the given array. So this position will be filled with that maximum small value, okay, some minimum value. Now we are at 6. Now we move forward with the 6. We check inside the hash map what is its index. It's 0. So we need 0 plus 1th element, that is first element. So the value will be 7. Now we are at 7. We check inside the hash map. Its index is 1. So we need 1 plus 1th element, which is second element, and that is 12. Now we are at 12. Okay. So what we do, we just check inside the hash map. Okay, its index is 2. What is 2 plus 1th element? It's third index element, that is 13. So we get the same way, and we can reduce the time complexity. So that can be done. Also one thing what we can do means we can just do a binary search, like this is the target, and we will be searching this target inside the sorted array. So since this is sorted, we are just making use, we are just searching in which index we are seeing this. So we can just make use of a binary search also. But here the hash map approach is pretty simple and straightforward. Let's also try this hash map approach with the next elements 6, 3, 9, 8, 10. 6, 3, 9, 8, 10. Okay. 2, 1, 15, 7. 2, 1, 15, 7. So we need a hash map with the key value pairs. Okay, and we are sorting this. So after sorting, we get 1, 2, 3, 6, 7, 8, 9, 10, and 15. And what are these indexes specified? Those are ranks. So this is rank 0, rank 1, rank 2, rank 3, rank 4, rank 5, rank 6, rank 7, and rank 8. Where 0 indicates the very small number, and 8 indicates the very last index indicates the largest number. So now we'll be also filling our hash map with these values. That is, 1 is having a value 0, 2 is having a value 1, 3 is having a value 2. Okay, 6 is having a value 3, 7, 4, 8, 5, 9, 6, 10 indicates 7, and 15. I'm just moving it here. Okay, 15 says 8. Okay, so we also have our hash map. Now we will be traversing the given input array. So 6, check inside the hash map where 6. So 6, it is at the value 3. Is 3 plus 1 greater than or equal to length? Here the length is, what is the length? 1, 2, 3, 4, 5, 6, 7, 8, 9. Length is 9. And 3 plus 1 is 4. 4 is absolutely less than 9. So what is the value at 4? It's 7. So that index will be filled with 7. Now 3. We check inside the hash map. What is the rank for this 3? It's 2. So we check whether 2 plus 1 is greater than or equal to length. 2 plus 1 is 3. 3 is not greater. So the next greater will be the element at the third index. So 6. Now for 9. Now we check inside the hash map. Okay. Now we check inside the hash map where 9 is in which index is 9, or which rank is for the 9. It's 6. So we check whether 6 plus 1 is greater than or equal to 9. No. 7. 6 plus 1 is 7. 7 is not greater than or equal to 9. So we just check what is the element at 7, and that is 10. So we fill that position with 10. Now 8. So we just check which is the position. 8. 8 is at 5th index. Okay. Is 5 plus 1 6. 6 is greater than or equal to 9. No. So what is the element at 6? It's 9. So that position will be filled with 9. Now we are at 10. Okay. What is the index for 10? We look inside the hash map. Okay. It's 7. So whether 7 plus 1, 8. 8 is greater than or equal to 9. No. So what is the element? It's 15. So we fill that 15 there. Now we are at 2. So what is the index of 2? 2 is 1. Okay, it's at index 1. Is 1 plus 1 greater than or equal to 9? No. 2 is not greater than or equal to 9. What is the value at index 2? Is 3. So that position will be filled with 3. Now we are at 1. Okay, 1 is at index 0 after sorting. So 0 plus 1 is 1. Is 1 greater than or equal to 9? No. So what is the value at index 1 in the sorted array? So 2. So we will be filling 2 there. Now 15. So what is the index at 15? Index at 15 is 8. Is 8 plus 1 greater than or equal to 9? Yes. 8 plus 1 is greater than or equal to 9. So this is the position where we will be filling our minimum value as specified in the question. Now for that we are going forward with the next element. So 7. So what is the value at 7? Okay, it's 4. The 7 is having a rank 4. So we need the 5th rank element. And 4 plus 1, 5. 5 is not greater than or equal to 9. So what is the element at 5th rank? It's 8. So 8. Let's confirm, like this is 7, 6, 10, 9, 15, 3, 2, the smaller value, and 8. So that's it. So that's our approach that we will be doing here. And we also see the big of n square approach, and also how we just make use of an extra space and made it big of n time complexity. Sorry, big of n log n time complexity, because we will be sorting. So sorting will of course takes big of n log n. So let's try this problem. If our given array is null, one thing to be noted is that we are assuming it's not specified in this array. We are assuming that every element will be like unique. Okay, for this problem, let's assume that every element is unique, but it's not specified in this. Let's assume like that. So if array is equal to null, or n is equal to 0, that is no element at all, let's say it's empty. Otherwise, what we need a copy array, and there is a clone method, in Java, which will just clone the given array. So we can just make use of that. So what this will do means all the elements in this array will be copied, will be available in our copy array. And now we are just sorting our copy array. Now all the elements will be arranged based on their ranks. So now what we need our map of integer, how we can name it, number to rank map, which is equal to new hash map. Okay, and we also need the result array, the greater array, and this array will be storing all the result. Okay, now let's fill our hash map. So for int I is equal to 0, I less than n, where n is the length of the array, I plus plus. Now we will be filling the hash map using the sorted copy array. So number, let's take the current number equal to copy array of I. So number to rank map dot put of current number comma I will be its rank. Now we are just traversing through this array, this given ARR. So for int I is equal to 0, I less than ARR, I plus plus, we take out the current number equal to ARR of I. So we just check which is the index. So int rank of current number is equal to, it can be obtained in fastly, like fast lookup, by making use of this hash map. So number to rank map dot get of current number. Okay, so the check that we mentioned, the first check. So what we are looking for, the smallest greater element, which will be the very next element in the sorted array. So first of all, we need to check whether the rank of current number plus 1 will go out of bound. Will it be greater than or equal to n? If that's the case, then our greater array, this case only arises if we are at a position where that current number is the largest among the given input array. So that means we have to put, let's copy this number. Okay, I'm just copying it. So then at that position will be that, otherwise our greater array of I will be copy array of rank of current number plus 1. Now we are done with our problem, and this greater array will be populated with what we are actually asked in the question. So finally just return the greater array. So let's just have a look on our complexities. So here we are sorting. First of all, we are making a copy array, and we are just cloning it and cloning the input array, and we are sorting this array. So this will give us an n log n complexity. Now we are again just traversing through the through the sorted copy array in order to track the rank of each number. So this will be having a time complexity of big of n, and we are again just traversing through the array. So this will also have a complexity of n. So the time complexity will be n log n plus n plus n. Okay, in altogether we can say it's n log n itself. For space complexity, if we are not considering, here I am not just considering the final result array, what I have is an extra space for copying all the elements. So I have a big of n extra space for storing this element, and also big of n extra space for the hash map. So my space complexity will be big of n plus big of n, which will be big of 2n, which we can altogether say it's big of n itself. So that's about time complexity and the space complexity. So let's see whether we are missing anything. Yes, okay, it's en. We definitely miss. Okay, minus 7, this is the very small value, 7, 12, 13. Yeah, let's also let's also see for this one. Okay, we are perfectly fine with our approach, and we can finally submit it, and this surely will pass our given test cases. As I told, like instead of this sorting, no, like we need sorting, sorry. Instead of making use of this hash map, like if you are just going through this element, okay, suppose we are checking, we took the current number. Now we search inside this sorted array by making use of some binary search, and can find the index. I don't know, like it just came into my mind now. So we can also approach like that, but here making use of an extra space in order to reduce the time complexity is also an approach. So that's our problem of the day.